Okay, Foundations in Pre-Cal 10. Let's get after it. Here we go. We have a video on solving systems. We'll get into what that means in a minute, but in this case, we're going to do it by graphing. So being able to graph, in our case, just linear equations, straight lines is going to be really, really important. When we get into this, you'll notice you don't need to necessarily graph the line, but at least know the points that exist on it. So let's have a look. So before we get to the graphing, what this comes back to again is a point a solution to an equation? And if you remember this from grade 9, we primarily used slope intercept form. And what we did was if we were given an equation, we plugged in an xy value for the xy, and the equation had to stay equal. And what that meant was that the point was a solution to that equation. So let's just look at that one more time. So now in this case, we're dealing with standard form. So we have 3x minus 2y equals negative 6, and we have the point 2 comma 6. So remember, that's an x and a y. It's a coordinate point on our grid. So we just plug in the x value here. So we're going to plug in a 2. And we plug in the y value here. So we're going to plug in the 6. And then we're just going to solve this out and see if it stays equal. So we end up with 6 minus 12. So negative 6 equals negative 6. So yes, this point is a solution to that equation, or it is a point that exists on that line. It works the same for slope-intercept form. In this case, we have y equals 2x plus 5, and we're going to sub in the x value of 1 and a y value of 8. And we're going to get 8 equals 2 times 1 plus 5, and you can probably already see that this is just going to give us 7. So if that happened, it was like, no, 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 we do not have a solution. So that would be a solution to one line. But when we get to a system, that means multiple lines. Now, in our case, we're going to be talking about 2 lines. So in this case, we have to try both. So you can see we have one line given here and we have one line given here. And the question is, do they both go through that point? And if they do, that would be their, wait for it, intersection point, right? Where the 2 lines intersect. So let's just test. We plug in a 5 for x, and we plug in a 2 for y, and that one should give us 17. So 15 plus 2 equals 17. 17 equals 17. Okay, good. Now, so we know that that point exists on the first line, but what about the second line? So 2 times 5 plus 3 times 2 should give us 17. 10 plus 6 equals 17. So, oh no, the point does not exist on both lines. So that point is not where the lines intersect. It would need to be equal for both of them. So let's try this one. In this case, now our x is going to be a 3 and our y is going to be a 5. So we have 2 times 3 plus 5 is 11. And yes, in fact, that is true. 11 equals 11. So that one's good. Now we check the second one. Remember, we're going to plug in a 3 there and we're going to plug in a 5 there. So 3 times 3 plus 2 times 5 is 19. So now we get 9 plus 10 equals 19. 19 equals 19. So this is a yes, yes moment, which means this point right here, 3 comma 5 on our coordinate grid, is where those 2 lines will cross. So that is what we are trying to solve for. That is what it means to be a solution to a system. So let's look at it graphically. Now, you'll see I mentioned before being able to graph is going to be important. Now, in this case, you could convert these into slope-intercept form, right? If you prefer to graph slope-intercept form, sure. It's not always going to be helpful if you don't get a nice y-intercept, but you could also keep them in standard form. Doesn't matter to me. What I will do is I'm going to keep this in standard form, and I like to solve. I'll do both. I'll leave the first one in. No, this one I'll do all in standard form. So when x is 0, right, that means that's 0. So if 2 times y is negative 4, well, that means y has to be negative 2. And then we do the same thing, except what about when y is 0? So when y is 0, well, that means that's gone. Well, so then x, it just tells us straight up x is negative 4. Now that's actually enough if you're confident that you didn't screw that up. You have a point here, and you have a point here. And what you can do is you can just continue to map your slope. So you go over 4 up 2. So 1, 2, 3, 4 up 2, or you could go down 2, 1, 2, 3, 4. Now, I'm not going to necessarily draw that line right now because I don't have a ruler, but you'll see why. Because now, what about my second one? Well, this is an easier table of values because I have no coefficients in front of the x and the y. So when x is 0, you have negative y equals 5. Well, that means that y is negative 5. When y is 0, well, again, this one just tells you straight up x is 5. So there's 2 points. So when x is 5, and then when right here. So you're probably looking at that thinking, okay, well, where do these things cross? And I will do my best. I do not have a ruler. I will do my best to draw a line through my points. Boom. And then draw a line through my points. And you can see right there. So they cross. Where do those lines cross? They cross at 2, negative 3. So by graphing, that tells us right there, 2, negative 3, that is the solution to my system. So use your ruler. Your ruler is going to be very, very helpful, and you want to make sure you're graphing them accurately. But there we go. And you can double check this by plugging in when x is 2 and y is negative 3. So if you did that here, well, when x is 2, you have 2 plus 2 times negative 3 should be negative 4. Well, that's 2 minus 6. Yeah, we're good to go. And this gives us 2 minus negative 3, which, yes, is 5. So we can double check using the algebra, but in this case, we're focusing on graphing. So let's look at another one. Now, in this case, what I'm going to do is I'm going to convert these things into slope-intercept form. So the first thing I'm going to do is subtract 2x from both sides. So now I have negative 3y equals negative 2x plus 3, and then divide by negative 3, divide by negative 3, divide by negative 3. And that gives me y equals 2 over 3x minus 1. Now this is a good time to use slope-intercept form because I have a true whole number integered y-intercept. So I'm going to graph this one in green. So I have my y-intercept at negative 1. And then my slope is rise over run up 2 over 3, up 2 over 1, 2, 3, up 2 over 1, 2, 3. And I'm going to continue by going down and negative as well, just to be clear on where my line extends. So there's my green line. And again, I'm not going to connect it right now, and you'll see why that might not be necessary. So I'm going to do the same thing here. I'm going to add 2x to this side, and I'm going to add 2x to this side. So now I have 3y equals 2x plus 6. Divide everything by 3. Now in this case I get y equals 2 over 3x plus 2. Now you might notice something interesting here. You have the same slope. So here's my y-intercept, but I'm going up 2 over 3, and I'm going up 2 over 3, I'm going up 2 over 3. So what you'll notice is if you have the same slope, remember from section 3, if you have the same slope, you have parallel lines. So these two lines are traveling parallel to each other, so they will never touch. So in this case, there is no solution. Okay, if you end up with two lines that have the same slope, but different y-intercepts, then you have two parallel lines, and they're never going to touch. No solution to that system of equations. So how about another? Again, I like converting it to slope-intercept form when I can, so I'm going to do that. So here I'm going to subtract 2x from both sides. We get negative y equals negative 2x plus 4. Divide everything by negative 1. Y equals 2x minus 4. So there's my first one. And then here I'm going to add 4x to both sides. So 2y equals 4x minus 8. And then divide everything by 2. So 2x minus 4. So you can see here, well, what has happened, you actually have the same line. So I'm not even going to graph these. I mean, you could, considering this is a video on graphing, why not? So the green line would go here, and then up 2 over 1, up 2 over 1, up 2 over 1, right, and continue. But the red line also exists here and goes up 2 over 1, up 2 over 1. So they're the exact same line. So what does that mean? Well, in the previous example, we had no solutions. In this one, we have infinite solutions. So those are the three scenarios. You'll either have a one point of intersection, or you will have no points of intersection, parallel slopes, or you will have infinite points of intersection when you have two equations that are actually the same equation, just written in different ways. So look out for all of those. Now, reminder, use your ruler to connect your lines. Start with just the points, because you might just find 2 points and they lie on each other, and then you're done. And then be prepared to use both standard and slope-intercept form to graph your line. If your y-intercept isn't a perfect number, a whole number or an integer, Then get your x-intercept, or if you can, from standard form, and then convert to slope-intercept form and map using your slope. There are some examples of that in section 3 as well. So have fun with this, but you got to be able to graph. All right, good work.